cover. It's windowing. And let me explain something about windowing. It's important. When you have a signal and it comes back to you and you want to extract certain information, any kind of signal, you can put it through a filter, quote. And filtering oftentimes is kind of, everybody thinks of LRC networks, or you think about now digital filtering, right? Where we're actually taking, or we're doing something where we have a difference equation or something like that. But there's another type of filter that's called windowing. Now what it means is this: you're going to take a portion of the signal that comes back to you, or is coming to you, and you're going to multiply it by a function, not for all time, just for a window in time. And that function is developed to do one thing: to extract properties that you're interested in. Now, I'm going to first tell you about a particular application to me, so you'll appreciate why this is important. It's not just some abstract tool. You don't need to write this down. I want you to listen. I deal with radar. And in radar, basically, if you want to write it down, you can, but you don't. I'm not going to test you on this. I want you to listen. In radar, basically, you have something that's an antenna, and this is really the transmitter receiver. It sends out a signal at a certain power level. It's a short burst, not very long, short. Comes out and there's a target out here. The target has a certain size. It's called the radar cross-section, and it's in meters squared. Don't worry about that. It's got a certain size. So the signal comes out, it hits this and comes back. If this is at a range R, and radar is an electromagnetic signal that moves at the speed of light, its radar is really range. It's radio wave and range in detection is really what it amounts to. But if it's at a range R, then you could say the total time of flight, well, it goes back. It first goes out, hits it, and then comes back. I think everybody understands that. So it travels 2R. Are you with me? So if you wanted the range to that, it would be 2R divided by the speed of light, would be actually the delta T. Does that make sense to everybody? C is the speed of light. If you take twice the range divided by T, if you got a reflection back then, that would actually be the delta T. So I'm keeping it as simple as I can. If this is the transmit signal and it looks like this, now actually, to make a long story short, this is multiplied by a very high frequency signal. Its width is tau, its amplitude is A. You don't have to worry about any of that. When you're looking at the return in real time, that's transmit. When you're looking at the return, you're going to get something that's staggered. And you're going to get a version of that. It'll have the same width, tau, and have the same high frequency, but the delay from here to here would be the delta T, so you can get range. Does that make sense to everybody? It's simple as I can make it. Think about an echo. Say something or clap your hands. If you're far away from mountains, you can hear an echo, a certain time delay. The speed of sound is the thing that's limiting it. You can figure the range to the mountains. It's very easy to do this kind of stuff. Well, electromagnetically speaking, this is going to be the speed of light, so that's 3 times 10 to the 8th meters per second. The times we're talking about are microseconds, possibly, maybe even tens, maybe hundreds of microseconds, but they're fast, all right? Now, another thing that happens with radar, when I'm looking at this, I get something called a Doppler shift. How many have heard of Doppler? When you think of Doppler, what do you think of mainly? There's one very good analogy if you physics. What? Say again? All right, yeah, really, you're talking about motor vehicles. The best thing I can think of is, you've ever been to an Indy 500 race or something like this, listen to the cars coming at you, their piston engines are going the same RPMs, you'll hear something like, and when they pass you, now what that is the wavelength lengthens and contracts because of the speed of the vehicle, changes it. The engine is not revving higher or lower usually, but that's the effect. Right? That's Doppler shift. It happens with electromagnetic energy too. I send out a signal, it comes back. Now, a lot of the things I deal with are, I'm interested in moving targets. I'm not interested in stationary targets. Let me explain why. If my radar is on the ground and I'm surveying an area, I know there's trees, mountains, and everything else that are reflecting back. That's clutter. The information they give me is nothing. But if something's moving, even though it may be a lot smaller in terms of its RCS, I would like to pick that up. So my interest is finding out what's moving. Police have that interest too. If you've ever gotten a speeding ticket, the way they did that with either KA band or possibly X band, if you got it more than 10 years ago, is they looked at the Doppler shift. Now, Here, they don't look in the time delay like that. What they actually do is take the signal they send, and just listen, don't write, just listen, and they look at what's called a Doppler spectrum. And if normally, this is in the frequency domain, I'm going to call it small omega domain. If the signal is unshifted, all right, if, in other words, if nothing's moving, the reflections you'll get will have a signature like this. I'll call this the magnitude, and I'll just use x of omega, and I'll call it square root 2 because that's a power signal, and I don't want to get too much involved in this, but what you're going to get is this. This is if it's not shifted, you get a sync waveform. The thing to note is the width of that main beam. Something else, if it's unprocessed, this will be in power 13.2 dB or in magnitude less than the main beam right here. That's called the first side lobe, right? Now, when you get a Doppler shift, now I'm going to say this with a Doppler shift, so I'm going to say, and now I have a moving target. What will happen is this whole spectrum is going to be shifted. If this is the frequency and we have to adjust for this, it would be called no velocity at all, no shift, all right? If the target is moving at you, it's a higher frequency, so this entire spectrum would be shifted up here. Now that should make sense to you. And this would be at omega Doppler. You don't have to worry about this right now. I'm just trying to give you perspective. Is everybody following this? Now this is done in the frequency domain, not the time domain. You understand that? And they look in the frequency domain. Now the difference between here and here would be the Doppler shift. Here's the problem. You don't get just that. What you get is this. You're going to get the main beam like this, which will be the scattering from nothing that's moving, in other words, from all the stuff in the area that's not moving, plus this thing superimposed on it. And I want you to understand something. If this isn't significantly sharp, if you can't see this with this background, then you don't know if there's a target there or not. So what they've developed, clever people that they are things called windows. When they take the signal that's returning, they multiply it in the time domain by another signal, and that signal will effectively bring these down from 13 dB to 43 dB or more or less. So they're basically, listen, if you think about this, what is 20 dB? A factor of 100. Does everybody follow me on this? If you're talking about 20 dB reduction in power, right? A factor of 40 dB is 10,000. 1/10,000th of the level of the main beam. Do you follow me on this? So it's a huge difference between 13 dB and 43 dB it actually goes down to. And that's what we want. Let me just finish my thought here. The downside is you don't get something for nothing. When we do windowing, you will reduce that side lobe down to 43 dB with a Hamming window. The problem is this main lobe is going to broaden and it will double its width. So that causes problems too. But I'm going to go through the windowing with you. That's the reason windowing is important. Follow me. It allows you to see characteristics that would otherwise be not observable without it if you just did raw data processing. Go ahead.
Do they just multiply by the Hamming window?
Yep, and I'm going to show you how. I'm going to go through it right now. Now that's the reason for it. I'm going to try to make this as simple as possible. This is chapter 9. And this stuff's very, very important. If you ever do anything with real-time data processing, with pulsing and stuff like this, remember Hamming window. You're going to need it to get anything meaningful a lot of times. And I could go on about radar, but take the class if you're interested. There's a lot of people. Right now, y'all know drone technologies and AI is like, it's the new horizon. Many of you people are going to be working in areas where you're going to be talking about probably very lightweight drones delivering packages, possibly completely automated cars driving you around, things like that. One of the big problems is sensors. Radars themselves are expensive, and there's a lot of other problems with them. What they want to do is take a radar, embed a signal in it so you can both communicate and interrogate the region. And there's other things, and I'll just say this, you can appreciate this. With radar, radars are what a bat does with sound, a radar does with electromagnetic energy. That's basically it. Now, the thing about a bat is he has a neural network that's unbelievable in his brain. He can tailor his chirps and everything like that, so it gives him a max amount of information, even texture about the region. With radar, we're not there. But there is something that you do, the bat doesn't, but it requires ambient lighting. You look and you don't transmit anything, but you receive all this reflected light, and you can tell distance by using binocular vision, by basically the neural net in your brain, your AI. You can tell, well, it's not artificial, it's real intelligence. You can tell the texture, you can tell what it is. I can tell that you're human, and I can tell that's a chair, because I've learned from the time I was born and looking, my brain figured these things out. It did pattern recognition at an incredible rate and other things. Now, think now. All this is ambient light, right? Matter of fact, if I changed the color light to red, you could still do it. If I changed it to blue, you could still do it. All of you could. All right? Why? Your brain. Your brain is trained, extraordinarily trained. You only have eyeballs as the receivers, and only 2 of them. But it's unbelievable what you can detect and differentiate. Now, take it a step further. This is optical, short wavelengths, right? Take it down to the actual frequencies of radars you use at microwave. All right, somewhere between 1 and say 80 gigahertz is very typical. All right, wavelengths from about say less than a meter to millimeters. All right, small wavelengths. There's a lot of energy out there. There's FM signals. There's the natural ambient radiation from the 2.73 KT from the Big Bang that's all over the place. There's all sorts of, quote, passive sources for microwave energy. In other words, that you're not creating them. And if you can teach a radar, passive radar, how to look at everything and pull out targets, not by transmitting, but by using reflected energy from other sources. There are passive radars. They're not that good, but they are out there right now. That is another generation, and that would be incredible. Now, some of you will probably be working on this right now. Most of that stuff is not with the antenna, so don't think it is. It's in the actual data processing, and it's in things that are yet to be uncovered. Algorithms are going to be developed, you know what neural nets are? If you've ever seen the Terminator, he was based on a neural net, all right? That's it, he's a learning machine, right? AI is really learning machines. And it's very interesting how they do it. I do some algorithms, genetic algorithms and things like that to do global optimization. Well, there's all sorts of things that go on. But think about that as an area of interest that you would like to do. Some of you are bright enough you can jump right in and do this kind of stuff. That is where this thing's going, because they would like autonomous vehicles that can think, deliver things, avoid birds, not get stolen, things like that. Be efficient, lightweight, the whole 9 yards. That's what they're doing. You know what Google is, right? Amazon, Google are probably, this is probably one of these things wrapped up real tight. You're never going to get anything out of them, but they're doing it. Our government's doing it. All the governments of the world are probably doing it. China is. They've got a huge thing. They're using that. They're using quantum computing. I could talk about that stuff. And I don't know, to this day I have a hard time with that, but I'm just going to tell you, because when you have to work at liquid helium temperatures, it doesn't seem to be very useful in the private sector, but there's a lot of things that are going on, and you're right at the cusp. When I was where you were at that time, what was the cusp? It was very large-scale integrated transistor projects that were predicted to allow computers, desktop computers, to be there. Like you have your laptop. It was not even possible. These gigantic, chunky things. But they didn't have liquid crystal displays or anything like that, or LED displays. We had these CRT displays. They're big and ugly and heavy, and we had nothing. What you've got there on your phone is more powerful than I had for my PhD work. So I'm just telling you, a lot is changing. But now you're on the cusp of what I've just told you about, what's happening. So think about that. 30 years from now, remember this. When you're looking back, just remember what I said. You can pick your path, but you have to do it soon. You have to sort of make a determination. I'm going to get interested in this, and I'm going to go with it. Because it is, it's something I can tell you. I'm not good at future predictions. People like Ray Kurzweil are futurists. They're better at this, but I know this is happening. I'm not sure exactly what direction it's going to take, but I know. So anyway, now to windowing. One of your tools in your toolbox to do some of these things that are so important. And this is chapter 9 information that's going to be interesting, hopefully. So, I told you about windowing, right? Now, I'm going to go through the most simple first thing. First, if I have any signal and I'm going to multiply it by something, the most common thing to multiply it by is just a simple square function. Where I'm going to say it's this. I'm going to say W, I'm going to just call this W of n is a window n, and its value is just 1. Call it a voltage. And that's for n greater than or equal to 0, less than or equal to L minus 1. So the signal has a length of L, and it's just square. And it's 0 otherwise. Well, that looks like a simple pulse waveform, doesn't it? It looks like a simple pulse. As a matter of fact, if you think about this, if you would graph it versus n, this is versus n, it's just this. And this would be, let's see, this is going to be, this point is just L minus 1, and this is 0. So that's all it is, versus n. It's literally taking a u of t minus a u of t minus tau and sampling. That's all. Or shifting a pulse waveform over, just skewing it. Now, if you have this, the next thing you have to take a look at is the actual spectrum. So if we talk about the windowed spectrum of this, and I'm going to do it with the DTFT. I was going to do it in continuous time, but it's easier to do it this way. I don't have to spend too many times on steps interval. So this is going to be equal to the summation here from n equals 0 to L minus 1 of the signal, which is just 1, right? That's x of n's value, times e to the minus j and omega. Some of you remember this, that the only thing this is going to boil down to, this looks like the dreaded what? The summation of a to the n goes from 0 to L minus 1 is really what? A to the 0 minus a to the L over a to the, or over 1 minus a, right? Y'all remember that? Here, a is going to be equal to e to the minus j omega. Do you follow me, everyone? Here, a, and this one is equal to e to the minus j omega. Now, that being the case, I'll do this one last time. I can say that this is going to be equal to 1 minus e to the minus j times omega L over 1 minus e to the minus j omega. I'm not going to spend much time on this. How many know where I'm going next with this? Raise your hands if you do. I know you do. I'm going to turn those into signs, aren't I? And then I'm going to have a phase shift. I'm going to do it fairly quick. So I'm going to factor out the top and bottom. Out of the bottom first, e to the minus j omega over 2. Then I have e to the j omega over 2 minus e to the minus j omega over 2. On the top, I have e to the minus j, and this is going to be omega L over 2. Then it's going to be times e to the j omega L over 2 minus e to the minus j omega L over 2. I do this for one reason. I can better see what this looks like, the shape of it. That's my goal. Here, I see that both this and this are sines. Do you all see that? Everybody see that? Give me a show of hands if you do. Right? Now, that means first upstairs, I'm going to have the sine. It's actually 2j times this, but there's a 2j down here that'll cancel. So I'm actually going to get the sine of omega L over 2 divided by the sine of omega over 2. That's just omega. Right? Now omega is from minus pi to pi. It repeats itself every 2 pi. And then you're going to get a phase, and the phase is just e to the minus j omega. And it's going to be L minus 1 divided by 2, because when this comes upstairs, it becomes positive. Now, that's the thing. It looks like a sync waveform, basically. And that is the actual envelope of this in the frequency domain. Do you follow me? Now, this is what you're going to have available to you when you do data processing and look at the frequency domain in real time. Now, what does this actually look like? Well, if you just take the magnitude of this, which I'm going to do right here, the magnitude of Wn of omega, this is a window with nothing else but itself. I just take a snippet. Basically, I'm multiplying a function by 1 over a time period, right? From 0 to L minus 1. And if you really want to know the time involved, it would be L times the delta t. That would be the length of time. The delta t is a sampling interval that I haven't specified. So now this really looks like just the sine of omega L over 2 divided by the sine here of omega over 2. That's the magnitude of that. That's an L. I chose L because the book used L. That's the only reason. So now we're going to revisit this. We've talked about this before, but it's important. I'm going to erase this part. So if I just take a look at this, this is without any modulation. I haven't even multiplied it by any signal. Just the window itself, what it looks like this. Please write this down. This you write down. This is omega here. Right here at the origin, it's 0. The only way to get that value, you can see the sign when omega is 0, you have sine of 0 over sine of 0, it's undefined. So you use L'Hopital's rule, take a derivative of the top and bottom, and evaluate it at omega equals 0. Do y'all remember L'Hopital's rule? When you do that, what happens is you pop out what? You pop out L over 2 on top and simply 1/2 on the bottom, so you get a height of L. That's the height of this thing. Now the next thing you have to understand is where the actual main lobe's width. It comes down to here. And the first 0 right here, I'm going to just do magnitude of that, and I'll actually do this. This is not drawn to scale, so don't get me on this. But the first 0 here, do you remember how you get that? Here's the trick with this. The sine of some small value is basically some small value. Like sine of x is about x in radians if it's small. By small, it means like pi over 20, something like that, pi over 30. Follow me? Up here I have a factor of L multiplying it. Now L is probably 50, 100, maybe 1,000, maybe 10,000. It's large, all right? This top part's changing very, very fast compared to the bottom part, all right? The first 0 occurs when the sine wave on top, the sine of omega L over 2 is 0. When is sine 0? Well, when omega is, sine of theta is 0, when theta is 0, right? And then when theta is pi, isn't it, class? Y'all with me? What about minus pi? That too, right? Sine is 0 plus or minus pi. That's called the first 0. Now that means the first 0 here would be when this argument is pi, and I can say omega L over 2 is equal to pi. I'm just putting the argument of the upper function. I've done this before. And then I can see that it corresponds to omega equal to 2 pi over L. So this point right here, for a simple rectangular window with nothing changing, this point is going to be 2 pi over L. Where do you think this point's going to be? Minus 2 pi over L. And that means the total width of this window, all right? That width is going to be equal to 4 pi over L. That's the narrowest possible width you can get. The downside of this is if you took a look at this value here, you would see it would be 13.2 dB less than this. Does everybody know what a dB is? If you don't, let me take you through it, just so you do. Because some people don't. The signal I'm talking about here is a voltage. It's akin to a voltage, not a power. You follow me? So that means when you're talking about dB, if I say anything in dB, it's 20 times the log of the magnitude of two quantities. In this case, it would be the magnitude of the first, which I can call that W0, over the magnitude of the second, W1. Now, I'm calling this magnitude W0 because it occurs at 0, and this magnitude W1. Follow me? We could prove this, but it's a way, it just sucks too much time to go here and do this. This one will be 13.2 dB. It means this is down by 13.2 dB. All right. Not significantly less, but less. Follow me in this class? Now 10 dB is what? Well, 20 dB is 100, 10 dB is 10, right? Isn't that right, Clyde?
That's right.
All right. Without getting stunned much, that's what happens here. Now, I want you to understand something. That this is just a base window that it's taking a snippet of a signal. Now I'm going to show you something that happens with radar. And I'm trying to keep this akin to things that I understand and I do fairly often. I want to relate it to things that I have the best shot of telling you about, because I do it So now that window, which isn't really much of a window, it just takes a snippet of a signal, right? If I multiply any incoming signal by this, what am I really doing? I'm just taking what? I'm sampling that signal over a certain length of time. I'm not skewing it or doing anything. Do you all follow me? So now follow me on this one. And you'll see these. Then you'll see why windowing is so important, hopefully. So, and I got to tell you one other thing with radar, so you understand. When you send out a pulse, right? As things come back, you take windows and you take the first window and you're listing and you get any information coming back, there may be none, and then you process it. You take the next window after that, process it. Next window after that. So you get a whole bunch of windows that process a whole bunch of information, and you do this in real time, and it's kind of interesting the amount of data you can get. But when you send out a radar signal, just keep this in mind. Terrestrial radar. As soon as you send it out, there's a possibility of it hitting the ground, it hitting anything, and getting a reflection. Do you follow me on this, class? So you're getting stuff back continually. The window will allow you to see the distance where all of a sudden the peak signal comes back. And it's really called signal and noise. But just try to understand, there's a lot to this. I'm trying to just strip it down to the bare essence, the things that you can appreciate. So now we're going to say, well, what happens to a window if there's a radar signal in there, all right? Now, radar signals at a very high frequency, and I'm just going to leave it as a magnitude. Suppose I say my incoming signal is now multiplied by this radar signal that's got 2 times, I'm going to say it's 2 times the cosine of omega, and I'll call this omega naught n, times my window of n. Follow me? All right, that omega naught is associated with a radar signal. It's very high frequency. And if you remember from before, that means it's 2 pi, right, times the actual frequency divided by the sampling frequency. Did you follow me on this, class? Without going into it, I just understand that's a high frequency signal. Now, what is this going to be? What's the transform of that? Here you think about your basic theory. Anytime a cosine or a sine multiplies anything, it really does what? It takes that signal spectrum of the window and it shifts it out to plus and minus omega naught. Do you all agree with me then? So now we shifted up and down this frequency axis. So now I take the spectrum I just did, and I'm going to get this. I'm going to get one at omega naught, and one at minus omega naught. And here, it'll look like this. And I'll write down the equation for it in a second. And basically, what I'm trying to do is show you this. What this really is, if I look at this signal, and I want the actual frequency domain shift to that, it's going to be 1/2 times 2, or just 1, and it's going to be times the sine of, now it's omega plus omega naught L over 2, divided by the sine of just omega naught plus, or omega plus omega naught over 2, plus the sine of omega naught minus omega naught, omega minus omega naught L over 2, divided by the sine of omega minus omega naught over 2. And that's really what I'm showing you here. This is the shifted spectrum of this. Call this x2 of omega. Y'all follow me? Now, remember, this width here is still going to be 4 pi divided by L. Are you with me? Got it? This isn't drawn very well. This next thing is 13.2 dB less, and there's another one that's 13.2 dB below there. But that's what you're going to get if you do a window on a radar return when nothing's moving. Do you understand? That will always be there. That's ground clutter and stuff like this. Can't get rid of it. Now, suppose I have a target that's got significantly less signal strength. Actually, normally you square that value. I just want to tell you, look at power. But for now, we're just going to look at the voltage, right? Now I have a target giving me a return. And the signal to target will have, with everything said and done, it's going to have this information in it that you can't get rid of it. That's coming back at the same time. But now my target has this spectrum. Target's out here, and here's where its main lobe is. but it's not at 13 dB, it's way down here. And now, here's the target. It's shifted in frequency, it's a moving target. You all see that? What I would like is to find some way to suppress this side lobe way down so I could see this target. Does that make sense to everybody? Now, a lot of this is a bit new because when I do windowing, it takes the actual signature, like this black thing right here, and windowing is going to do something. It's going to suppress this side lobe from 13 dB all the way down to 43, as much as 58 dB. The downside is it broadens this a little. This isn't drawn to scale, but the windowing is going to allow me to do that. Are you listening to me? Yes, sir.
Does it also reduce the shifted peak?
It will not. See, this peak and this peak stay the same. What will happen is these go away.
Okay.
So everything, basically, you're absolutely right on this. The signal that's also shifted in frequency has the same effect on it, proportional, all right? Which is the idea. Now,
Okay.
so now with windowing, I'm going to show you what I've got here. So let's take a look at a couple. I'm going to do the one that'll make, this is sort of a step towards the right direction. I hope you'll appreciate this. There's so much to this, but it's important at least you appreciate the basics. It'll really help you. So now, that's a basic window. Now the next step up, this is, by the way, the evolution of this is interesting. This came, I believe, from the radar world, but I say that with hesitation. I'm not absolutely sure. So the next window they try is this. They say, I'm going to try a triangle window like this. Well, in time domain, this would look like a triangle, right, with tau, right? And it'd be shifted, and there would be some point t there, and this would be some t minus tau over 2. It'd be shifted out to a point there because this is the 0 point. Do y'all follow me on that, class? And this would have a height 1. The first one was just a pulse shifted, wasn't it? Now that's in continuous time. In discrete time, that signal is remember how this signal would be represented? If I had this tau of t, a simple triangle, it's what? It's 1 minus 2 times t over, it's actually magnitude of t over tau times the pulse of with tau of t. That's the representation. That's the mathematical statement of an unshifted triangle, right? Then when I shift it, what I have to do is put in t minus tau over 2 there, and this is t minus tau over 2. And now that shifts it out right here. That's the only thing I'm doing. Do y'all remember this? If you don't remember it exactly, try to appreciate the fact I'm trying to draw from your understanding of continuous time waveforms. So for discrete time waveforms, the window looks like this, the triangle waveform. And I'm going to call it this of n. And it's of width L. The book doesn't. And the way he writes it in his book, it's 1 minus 2 over the quantity L minus 1 times the magnitude of n minus the quantity L minus 1 over 2. And I did this on purpose up there so you could see the pattern. All right, you'll notice the 1, right? Now there is no pulse multiplying this because it's assumed that this is only good from 0 to L minus 1. That's it, and it's 0 else. I could multiply this whole thing by pulse, but I don't need to. Follow me on this, class? You don't need to. You can just make this explicit statement. It's 0 for any other time. Now, when I have that, if you look at the parallels, there's 1, there's the 2. Tau is L minus 1. It's the width of the signal. Do you follow me? It's the literal time on time. Then this, n, is proportional to t. This is really the width divided by 2. L minus 1 over 2 is really the width by 2. Do you follow me in this, class? So that replicates a sine, or this triangle waveform, only it does it like this. Now you're going to have discrete values, like so. All right? That's the only difference. That's for discrete, that window. Without going through the data processing, I want to tell you something about this particular thing. This will broaden in the frequency domain. What you get is this. If I look at the omega domain, and this is my main height, it will be L. But now what happens is this. this main lobe doubles. Now this will be at 4 pi over L, and this will be at minus 4 pi over L. So the width, total width of this signal is actually equal to 8 pi over L. This is going to be something that stays with you. The benefit of that is the sideband right here. Now this sideband right here is going to be down not by 13 dB, but it will go down to 27 dB. It's minus 27 dB below this. If you think about it, 30 dB is a factor of 1,000. Do you understand? So this is bringing down the signal by a factor of 1,000. It's significant, in other words. The power is down by a factor of 1,000, that side lobe. The side lobe, now all of a sudden, this window, just this triangle window, if it's used properly, will allow me to see a lot of targets I couldn't see before with the Doppler shift. Got to tell you one other thing proportionally. It's hard to appreciate the width of this thing. And if I had time, I'd get into the Doppler, the reason why this is so important. You'll see that the longer that time is, as L gets larger and larger, the narrower that window gets. Do y'all follow me? There's a downside with radar. The longer the pulse is that you send in terms of its on time, the less the range resolution is. You can't differentiate small targets. You can't see how many targets there are because the returns will overlap. Just trust me on this one. There's always a trade-off with radar. When you think you can get something for nothing, you can't. You just can't. But nevertheless, this is something to be aware of. And if you take Dr. Reeves's course in digital signal processing and digital image processing, you will find out a whole world of things that you will appreciate with the reason it's so powerful. All right, now, next, so this is a step in the right direction, but it's still not enough. And I can speak from experience. This will not do it for most of the stuff that we need moving target indicators on. So then you get into the area of a lot of brilliant mathematicians like Gauss and stuff. Gauss, before radar was even developed, he was already playing with this stuff. And he found out that, well, let me go to the Hanning window. Now this is the one that really showed the best promise. Remember, a lot of this stuff was developed before they had global optimization algorithms and things like this. There were basically people that were flying the best they could. They had a lot of tables, a lot of mathematical knowledge. They could do standard types of, minimizations. But you know what global minimization is? You know the difference? There's local and global, right? If you have something like this, and I ask you for the minimums, you say it's there. There's a whole bunch of them, right? The maximums, there. They're all relative. Take the derivative of this thing versus distance. You would find out wherever it's 0, you would have either a min or max, right? But you have a whole bunch of them. So how do you find the global minimum or the global maximum? Well, first you have to find all of them. What if it's an uncountable number? Well, then you got a problem, right? Well, that's the kind of things that global optimization algorithms do. They find the minimum of all possible minimums or the maximum of all possible maximums, and they do it in a very clever way. They didn't have that available to them. So they just basically were very clever, and they saw patterns. The next thing they saw was something, the next one that was really a step in the right direction was called a Hanning window. And actually, I don't know the year that this was created, but it's called a Hanning window. Now this one's interesting because now it's going to say if the signal I have is of length L, this window is simply 1/2 minus 1/2 times cosine of 2 pi over L times N. It's L minus 1, pardon me. L minus 1 is the width of that thing. Now I want to tell you about this one. What it looks like is this. If I have this waveform, where I want a value of 1 here, at the middle, which is going to be, it's simply going to be pi over L minus 1, and this would be pi, 2 pi here, and I put this in degrees, then this will do it. You notice when n is 1, the when n is 0, the cosine of 0 is 1. I have 1/2 minus 1/2. It starts at absolute 0. It goes to relative maximum right at the center. And then at the end, it goes to 0. All right? And that's the value of this thing for n greater than or equal to 0, less than or equal to L minus 1, and it's equal to 0 else. All right. So it's just taking a snippet. You take this, multiply it, then all the information, you're going to multiply that by the incoming signal, you're going to store it. Now, the nice thing about this, I'm just going to show you what it does by itself. Remember, all the waveforms I show you when they're multiplied by a cosine waveform are shifted out to plus and minus omega naught. All right? Just remember that. I'm just showing you the baseband waveform, or the unshifted waveform. So this one is the really nice. It has the same width as the triangle. It's still going to be 8 pi over L in total width, but now the side lobes are really down. This is going to be down by 32 dB, from 27 to 32, 5 more dB. The final window, how many have heard of these windows in any way, shape, or form? Where did you hear about it? You?
Use them during internship.
Okay, what about it?
What? I think I saw Hamming in the book once.
Did you have
It was used in one of the Digitron labs for the signal.
Hamming window?
Yeah.
Did you guys have Digitron? How many have digital electronics now? Did you use which? Did Dr. Young use it? He used the Hamming window? You required it?
It was during one of the labs that had us build a radio. You had to use a
Oh yeah.
Hamming window.
Okay. Never mind. That makes sense. You'll need that. Was that software defined radio? Yeah. How many had software defined radio left? You did it? Right? Didn't you all do it?
Not this year. We don't.
I played CAD. I mean, was that when we had 2 wires and we just held close to each other?
Yeah. I remember holding 2 wires next to her with squiggly lines.
Don't ever say that to people you interview with.
There's not a whole lot of
That's not what
anything on that.
All right. Well, the final one is called the Hamming window, and this is the best of the best. It's the one that you get the most bang for the buck. And the only thing that changes are the values in front of the coefficients. Here, instead of having 1/2, you're going to have 0.54. This is in the book. And instead of having 1/2 here, you're going to have 0.46. Now let me explain one thing about this one. This has the greatest reduction in side lobe without increasing the main beam width from that of the triangle. So it looks like this, and I should just left that up there. This is in the book. If I take a magnitude of x of omega for the Hamming window, this is with the Hamming window, here the main beam width is still going to be equal to 8 pi over L. The side lobe reduction goes down to minus 43 dB, which is remarkable. Minus 43 dB is better than a factor of 10,000. It's way, way down there. At that point, all right, effectively, the only thing you care about is this width, because that's so far down. If you get any kind of a reasonable shift in frequency, I mean, shift that out this way or that way, even though that's going to be the ambient, it's still going to be from just the stationary stuff. The reflection, you're going to be able to see that moving target. And that's the most common window that I know of used today in radar. And remember that, yeah, the Hamming window. Now, some of you are going to say, well, what about a quiz on Friday? All right, I'm going to ask you this. How many want a quiz on Friday? Raise your hands. How many do not? Raise your hands. All right, then you won't get one this Friday. But I may ask you to hand in some homework. I may, depending on the behavior of the class overall. I'm going to give you some homework, and I expect you to do it. But if I see everybody blown off on Friday, then I'm going to collect it.
Wait, you collected it for me to 10?
Huh?
Would it be a 10 quiz? You collected it.
No, it's going to hurt you if you don't turn it in. If you don't turn it in, you get clobbered. It's going to give you the answers to it. I mean, what else can I give you? All right. In other words, I'm going to allow you to know what the answer is, but you must be here. So if I collect it, if somebody turns it in from somebody that ain't here, I'll sue them. All right. That's basically it. Now, Friday, listen, I'm going to do a review, and I want you to do me one favor. If you have questions, think about it, come prepared. Send me the questions in advance if you want. Remember, we've got a lot of stuff that it's going to be able to find. It's comprehensive. Convolution, all the way down And if I give you windowing, I would give you the equations, all right, just so you know. I'm not gonna ask you to come up with it.